Right, in this picture, there are two masses, 3 kilogram and 2 kilogram masses. 2 kilogram mass is hanging by there, a thread. It's going over a pulley and it's being supported by the weight of 3 kilogram, and there is a frictional force. The coefficient of the friction, if you realize, it's about it's 0.3. The masses are given, so first highlight what you are given, right? So I would say, so that's 2 kilogram there given, 3 kilogram given, light string that passes over, so there is a, right, this is the string, so when that happens there is a tension, you can call that T1, and there is another tension that's, acting this way, that's gonna be, let's say, T2. The difference in the tension, these are basically the forces, right, times the radius of the pulley, right, that's force times distance minus force times distance gives you the torque. That's the main idea here. So when you have this situation that's happening, when tension equal T1 tension equals T1 equals to T2 second tension, then in that case both balances out, so the torque will be zero and the wheel will not rotate. um, anyway, so the moment of inertia is given here, right? The moment of inertia I for the wheel, the moment of inertia is given as 0.00004 kilogram meter square, mr square basically, 0.004, I'm gonna write it like this way, meter square. And the radius of the wheel is 5 centimeter, 0.05 meter. The coefficient of the friction over here, the coefficient of the friction equals to 0.3, and as you know, because it's trying to go this way to the right, the frictional force will try to pull it the other way around, so the frictional force would be mu times, in this case it's not an inclined plane, it's a horizontal plane, and therefore the normal reaction equals to the weight, so mu times n, that is the frictional force. I'm just gonna not write the subscript at the moment. That equals to mu times that n is mg, let me call that m1 so that it's easier to handle later, m2, so that would be m1g. That's the frictional force that's trying to stop this block from sliding down, right? When you release it from the rest, because of this force over here, the force of the gravity m2g, that basically gonna uh, cause the acceleration going downward, right? Let's call that a, and because of that force, m2g minus t equals to a, if you think of that way. So it's basically gonna cause it to rotate downward. We're gonna work this problem. I mean, there are two ways to do this. I think um, the energy way is probably the easiest one, so I'm gonna just work it out energy way. You can, try the other way where you would basically equate the forces and then find the dynamics, where use the kinematics to find the speed of the upper block. So let me just try to work it out with the energy. Okay, energy method. If you wanted to look at the energy, right, you have the kinetic energy and you have the potential energy, right, u. So kinetic energy for first block initially, it's gonna be 0, right? And the potential energy, suppose that's where you started, right, and you're gonna go down. So, and then because it is gonna rotate clockwise, I'm gonna say that down is negative, so that's gonna be minus h. So I can set the potential energy to be 0 initially, and that's true for both of the masses, first mass and the second mass, right? So we're gonna write that for the first mass and for the second mass, m2. Okay, this is second body, I'm sorry. And when it moves, um, that's going to be different condition, but for the moment the kinetic energy is 0, potential energy is 0. Okay, and then it has to move across, right? When you move across, there is going to be some work done, and then that work done is supplied in the form of the energy. So initially there is no kinetic and potential energy. However, you have to do the work. Okay, so you have kinetic energy, potential energy. Okay, um, and then after it moves, I'm gonna look for the non-conservative force. There is gonna be kinetic energy, right? For first mass, it's gonna be half mv square, right? And for second mass, it's gonna be half m2v square. Notice that I have written v in both cases because both of them are going to travel with the same speed in this case. The potential energy for the first one is still zero because it's not changing any ground here, right? But for the second case, it's gonna be minus mgh. It's going down, okay? And this is the net energy where you have the first and the second kinetic energy and the potential energy. Where does this come from? If you imagine that, it was basically being supported by the work that you have to do against the friction. So initially you are basically supplying the some part of work done that as one of the source of the energy here to basically compensate for that. And it's non-conservative work that is being done so that you can, whenever you overcome it, you're doing the work and dissipate the energy in the form of that. So this is the energy conditions. If there was no friction, that would be end of it, right? You have the kinetic energy, you have the potential energy, kinetic energy, potential energy, and that's it. Do you think that's enough for this problem? No, because there is wheel here. This is not an ideal pulley. It's given with a moment of inertia, right? So the moment of inertia is given, right? And then whenever it rotates, right, it's gonna do the work. And the kinetic energy of this rotation is given by half I omega square. Okay, so for the wheel, you have of course potential energy we're not going to consider, but initially it's not rotating, but finally it will rotate half I omega square. Okay, the moment of inertia is given. However, if you notice this formula, v equals to r times omega, you can substitute that value over there, right? So omega equals to not w, right? Omega equals to v over r. So therefore you see that the total energy now is because of the linear motion, right, and because of the rotation of the wheel. So you have to spend some energy to rotate the wheel as well. Okay, now if you think about this situation here, you can think of total energy before and total energy after, right? So, and that the difference in the energy, E, difference in the energy, right, delta E, that must be
It's
zero.
8:30.
Thank you. That must be zero if it was a frictionless surface, but you see that there is friction, omega mu equals to 0.3. Therefore the difference in energy is basically used to do the work, right? And that work is non-conservative in nature. Okay, it's 8:30 in the morning, so forgive my handwriting. um, I'm in a conference. So work is non-conservative here because it is work done against the friction, right? That's gonna be the force, that is frictional force that you have here, times the distance. How much did it go? It says it goes through the distance of 0.6 meter, right? Is that right? Is that right? Yes. That's equals to, the force is mu, right? It's dragging the first mass, m1 g, times the distance is x. So this is the work done by non-conservative frictional force, right? And it's basically gonna be compensated in terms of the change in the energy. Okay, so basically you're gonna write down, for example, the kinetic energy of the second mass, right? and that's initial minus, sorry, final minus initial, or you can go initial minus final, and then the kinetic energy of the first mass, right? That is the difference in kinetic energy of the first mass, second mass, the difference in the potential energy of the first mass, difference in the potential energy of the second mass, right? And then the difference in the rotational kinetic energy, right? This guy over here, that gives you the difference in the energy. Okay, difference in the kinetic energy, difference in the kinetic energy over here, and that is difference in the potential energy, difference in the potential energy for the both of the bodies, and then the difference in the rotational kinetic energy. This part, don't miss this part. Okay, so if you solve this equation, you should be able to obtain the value of the velocity, keeping in mind that omega equals to v over r. So over here you have to substitute the value of omega in terms of v and r, and the question is asking for the velocity. So you have the same velocity here, same velocity there, and over here, if you look carefully, this half I omega square already has, that is equal to half I omega is v over r, so that's going to be v square over r square. Okay, so this is, there is a v, there is a v, and there is a v. We will take that common factor out, and then work out the way. Okay, this is a hint. So hopefully you can solve this.